States of matter. Introduction. Matter possesses some mass and volume. It is composed of tiny atoms and molecules. Depending on its temperature, matter can exist in three states: solid, liquid, and gaseous. The existence of matter in different physical states is due to the interacting attractive and repulsive forces among their molecules and atoms. The intermolecular forces keep the molecule together, while thermal energy moves them apart. Some characteristics of solids, liquids, and gases. Solids: definite shape and definite volume, rigid and do not flow. The intermolecular force of attraction is maximum. Kinetic energy of molecule is least. Liquid: definite mass and volume but no definite shape, less rigid and can flow. The intermolecular force of attraction is less compared to solids. Kinetic energy of molecules is large. Gas: neither definite shape nor volume but definite mass. No rigidity and can flow easily. Intermolecular force of attraction is negligible. Kinetic energy of molecules is very large. Gases undergo diffusion with faster rate than liquids. Different gases diffuse into each other to form homogeneous mixture. Gases have high expansion power and high compressibility. Gases exert pressure on the walls of the container in all the directions in which they move. The density of gases is lower than liquids and solids. Measurable properties of gases. Mass. Gases possess mass. Mass of a gas is determined by first weighing empty container and then with gas. From the difference in the two weights, mass of gas in grams or kilograms can be obtained. Volume. Volume of the gas is the space occupied by gas molecules. That is the volume of the container. The SI unit of volume is meter cube. Temperature. It is a measure of internal energy content. It is measured in Kelvin, K, or degree centigrade and degree Fahrenheit. K is equal to degree Celsius plus 273. Pressure. It is the force exerted by the gas molecules on the walls of the container. The SI unit of pressure is Newton per meter square or Pascal, PA. 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 76 centimeters of mercury, which is equal to 1.0132 into 10 raised to 5 Pa, which is equal to 101.32 kPa, that is kilopascals. Density. Density of a gas. Density of a gas is its mass per unit volume. The SI unit of density is kilogram per meter cube. Diffusion. The process of spontaneous mixing of two or more gases to form a homogeneous mixture, irrespective of their temperature, pressure, and densities, is known as diffusion. The rate of diffusion is equal to volume of gas diffused upon time. The rate at which gases diffuse into each other depends on their molecular mass. Gas laws. Boyle's law. Statement. The law states that the pressure of the given mass of a gas varies inversely as its volume at a constant temperature. P is inversely proportional to 1 upon V at constant temperature. P is equal to K upon V. PV is equal to K is equal to constant. P1V1 is equal to P2V2, which is equal to constant. Charles' law. The law states that the volume of a given mass of gas increases or decreases by 1 upon 273 of its volume at 0 degrees centigrade for every degree rise or fall of temperature at constant pressure. Vt is the volume of the gas at T degree Celsius. Then Vt is equal to V0 plus into bracket V0 into T upon 273 bracket complete, which is equal to V0 into bracket 1 plus T upon 273 bracket complete, which is equal to V0 into bracket 273 plus T upon 273 bracket complete, where 273 plus T is equal to Tk and 273 is equal to T0k. Therefore, Vt upon T is equal to V0 upon T0. Thus, Vt upon T is equal to constant. Therefore, V is directly proportional to T. Therefore, V1 T1 is equal to V2 T2, which is equal to constant. Absolute temperature scale. The lowest temperature at which all gases theoretically occupy zero volume is known as absolute zero temperature. It is also known as Kelvin scale. 0 degrees Celsius is equal to 273 K. Tk is equal to T degrees Celsius plus 273. To convert from Celsius to Fahrenheit, or degree Fahrenheit is equal to 9 upon 5 degrees Celsius plus 32. Degree Kelvin is equal to 0 degrees Celsius plus 273. Ideal gas equation. The mathematical expression which is used to study the combined effect of pressure and temperature on the volume of gas is called the general gas equation. The general gas equation is P1V1 upon T1 is equal to P2V2 upon T2. PV is equal to nRT for n moles of gas. It is the ideal gas equation. Dalton's law of partial pressure. Statement: the total pressure exerted by a mixture of non-reacting gases is equal to the sum of the partial pressures of all the gases present in the definite volume. For example, if P1, P2 and P3 are individual pressures of gas known as partial pressures, then the total pressure P of the mixture of a gas at the same temperature is given by P is equal to P1 plus P2 plus P3 up to Pn. Graham's law of diffusion. Statement: the law states that under similar conditions of temperature and pressure, the rates of diffusion of gases are inversely proportional to the square root of their densities. R is inversely proportional to root D. Consider two gases A and B with their rates of diffusion Ra and Rb, while their densities are dA and dB respectively. Then, at the same temperature and pressure, Ra is inversely proportional to root dA and Rb is inversely proportional to root dB. Therefore, Ra upon Rb is equal to root dB upon root dA. We know that dA is equal to Ma upon 2 and dB is equal to Mb upon 2, where Ma and Mb are molecular weights of gas A and gas B respectively. Therefore, Ra upon Rb is equal to root of Mb upon Ma. Therefore, Graham's law may also be stated as follows. Under similar conditions of temperature and pressure, the rate of diffusion of gases are inversely proportional to the square root of their molecular masses. Rate of diffusion R is equal to volume of gas diffused upon time taken for diffusion. R is equal to V upon T. Liquid state. Properties of liquids. In a liquid state, intermolecular attractive forces are stronger than gases, but weaker than solids. Liquids do not have a definite shape, but take the shape of the container. The density of liquid is much higher than any gas. Due to the smaller size of their intermolecular voids, liquids are almost incompressible. The molecules of liquids are in constant random motion. Different liquids flow with different rates due to difference in their molecular friction, which is known as viscosity. Liquids undergo boiling at specific temperature known as boiling point of liquid, at which vapor pressure of liquid and the atmospheric pressure are equal. Vapor pressure. It is defined as the pressure exerted by the vapors of liquid in equilibrium with the liquid at constant temperature. It depends on the nature of the liquid and temperature. When rate of evaporation and condensation becomes equal, that is, when equilibrium is attained, at this point the number of molecules in gas phase remain constant. The pressure exerted by these molecules on the surface of the liquid is called vapor pressure of the liquid. Surface tension. It is defined as the amount of energy required to increase the surface area of the liquid by 1 unit. This is called as the surface tension of the liquid. It is also defined as force acting per unit length perpendicular to the line drawn on the surface of the liquid. The SI unit of surface tension is Newton per meter. Viscosity. The internal resistance to flow in liquids which one layer offers to the other layers to pass over is called viscosity. The SI unit of viscosity is poise, P. 1 P is equal to 0.1 Newton seconds per meter square. It is also defined as the force of friction between the layers of liquid, or viscosity is the measure of resistance of liquid to flow. Viscosity is related to intermolecular forces of attraction. If the intermolecular forces are large, viscosity will be high. For example, honey is more viscous than water. As the temperature increases, the viscosity decreases because of the decrease in the intermolecular forces of attraction. Classification of solids. Solids may be classified into 4 types. Molecular solids. The solids in which constituent particles are molecules are called molecular solids. These molecules are held together by weak van der Waals forces. They are soft and easily compressible. They have low melting points. They are bad conductors of heat and electricity. They are volatile and have low heats of vaporization. For example, ice, urea, naphthalene, solid carbon dioxide, iodine, phosphorus, sulfur. Ionic solids. Ionic solids are three-dimensional arrangements of anions and cations held together by strong electrostatic force of attraction. Thus, in ionic solids, constituent particles are ions. They have high melting and boiling points. These are hard and brittle. They have high heat of vaporization. They are poor conductors of electricity. These are generally soluble in water. For example, NaCl, CuSO4, MgO, AlCl3, KNO3. Covalent solids. The solids in which constituent particles are held together by covalent bond are called as covalent solids. These are also known as network solids. In these solids, constituent particles are atoms. They have high melting and boiling points. These are poor conductors of heat and electricity. These are hard solids. For example, diamond, silica, boron, etc. Exception is graphite, which is soft, though it is a covalent solid. Metallic solids. These are solids consisting of positively charged metal ions which are embedded together in the sea of delocalized electrons. The forces present between the constituents are metallic bonds. They are good conductors of heat and electricity. They may be hard or soft. They have metallic luster and color. They are malleable and ductile. For example, Na, K, Al, Zn, etc.